Hi, I'm Satyajit Das, and in this video, I'm going to give a very quick walkthrough of the BSc code base. So, this is not meant to be very well in depth or structured, but I will give you enough information so that you can start digging much deeper into the BSc code base and understand on your own, and basically have a decent idea about which are the components and where they exist. So BSC in a nutshell for now. So it started as a fork of Go Ethereum, and it was initially very similar to the way Ethereum operated, with mainly some parameter differences and the difference in consensus mechanisms. But currently there are a lot more differences between Ethereum and BSC. And before I proceed in this video, I'm assuming you have knowledge of Bitcoin, Ethereum, or blockchain in general, because there are certain concepts of blockchain which I will talk about and explain where they are in this code base. So I expect you to have some prior knowledge to this. In case you don't have the knowledge and you are a complete beginner, then please refer to the links I have given in the description to brush up your knowledge. Okay, so when it comes to the code base, there are two ways to look at the code base, mainly because there are two types of players in the blockchain ecosystem. So the first one is the validators or the nodes, and the second one are the users. So to create a blockchain, to have a blockchain network, you need to have validators or nodes, which are essentially taking part in the blockchain ecosystem and making the blockchain as a whole available. And then on the other side of things, there are users who send transactions or who have tokens like BNB or Ether, and who send transactions to create smart contracts or interact with smart contracts. So I will explain the code base from the point of view of nodes as well as users, so that it will make more sense when you start looking and dig deeper into the code base. So for validator point of view, there are like these are the following concepts. So there is this CMD folder which I will show, which is essentially the entry point of the code base. So that's the command you give to actually start the blockchain and join the blockchain as a whole. Then there are like P2P packages, because blockchain nodes need to talk to each other. Then there's the actual blockchain package itself. There's miners, so you have to mine. There's a process called mine to create blocks. And then there is a consensus and execution side of things, and there are like handlers. So that's from the node point of view. So from a user point of view, there are things like sending a transaction, and then ensuring the transaction is getting into the TX pool, and followed by subsequent mining, through which the transaction actually becomes a part of a block. Then the transaction should be propagated across the peers and ensure that it reaches inside a block. So that's not what a user directly does, but it is important for the user to know these concepts, so that whether his transaction actually became successful or not, that depends on if the propagation of transactions happened correctly or not, and whether the transaction made into a block or not. And then there is this writing of actual blocks in a blockchain and persist it. So these are the two ways of looking at the code base. So now let's dig deeper into the code base. Okay, so this is the main repository of BSC. As you can see, github.com/bnbchain/BSC. So there are like several packages here you can see. I'm going to start off with this CMD folder, the command folder, from a validator or a node point of view. So once you open the CMD, you have these several subfolders, as you can see. The important one is Geth. So when you are starting the blockchain, you are essentially executing this main.go file inside Geth. So this is the main.go file, and here you have certain flags. And essentially the main function is running this app.run. Okay, and this eventually runs this Geth function. So as you can see, Geth is the main entry point to the system, and if no special subcommand is run, so unless you are doing a lot of customization, so by default this is what is run, and it creates a default node. Okay, so there are two key things here. There is this make full node and start node. So here you are creating a node and you are starting the node. Okay, so let's dig deeper into these. So make full node creates a node. Okay, it gives you back a node, so which is of type node.node, and it gives a backend. So let's see what these are. So node is the container in which the services can be registered. So that's the node. And then we have ETH_API.backend, and inside this backend, it is an interface essentially, and it has to provide certain functionalities. Like it should have its own chain and chain DB, which is the database. The chain itself is the blockchain, and there are several RPCs and things related to the blockchain API. So like if you can query header by number, header by hash, current block, block number, block by hash, etc. And transaction pool API. So things like send transaction or get transaction and various other things. This is what make full node is about. And then you do the start node. So start node boots up the system node and all registered protocols. So here we call this function to actually start the node. So utils.start node. And here we are calling this node.start function. In this start node, let's see where these key variables are used. So this is the stack and this is the backend. So this backend is used here where we are converting into this ETH backend type, and at some point we're actually starting the mining process. So we are calling here ETH backend dot start mining. So what start mining does, it starts the actual mining process, which involves creation of blocks. So creation of blocks involves pooling the transactions, checking the transactions are fine or not, actually writing those transactions and creating the blocks. So let's see the start mining function. So start mining starts the miner with a given number of CPU threads. If mining is already running, it adjusts the number of threads. And at some point it checks if the underlying engine, the consensus engine, is of type Clique or Parlia. So in BSC we run Parlia. So in this case, this should work. Then eventually this miner.start gets called, and this start function gives a channel notification to this start channel, okay, of the miner. So this start channel is indicative of starting. So we are ready to actually start the mining process. And this start channel is, inside this for loop, infinite for loop of this update function. And whenever this start channel is called, then this worker gets started, and there are certain other things that get started, like this worker element, and the worker start channel gets executed. So in this case, there's this struct called worker. So worker is the main object which takes care of submitting new work to the consensus engine and gathering the sealing result. So you create a block, then you actually seal it, then you are sure of its authenticity. So there is this start channel where when this gets notified, then this commit function is called, and then eventually we are submitting some new work. So new work is submitted to this new work channel, and this new work channel is eventually calling this commit work. And this commit work has, what does it do? So commit work generates several new sealing tasks based on the parent block and submits them to the sealer. And it eventually calls this prepare work. And here prepare work constructs the sealing task according to the given parameters. So it finds the parent, then does the work based on the parent. It creates the header here and checks what kind of hard fork is it, if it is London hard fork or not. So accordingly it will execute EIP 1559 or not. And then it calls the prepare function of the underlying consensus engine. At some point it creates this env variable, so make env. So what is make env? It gives back something called this environment, and inside this environment we have the transactions. Okay, so what is environment? Environment is the worker's current environment and holds all the information for sealing the block. So here eventually the transactions end up. Okay, and these are the receipts, and there are also sidecars. So if you're aware of what is EIP 4844 or proto-dank sharding, you will know what block sidecars are. Otherwise, I'll put a link to a video explaining what this concept is. So for now, we are only concerned about the transaction. So let's see what a transaction looks like. So transaction is here inside this core/type/transaction.go. So transaction is the Ethereum transaction, and there are like various transaction types here. So these are like transaction struct is extendable to various types. We can build on top of the previous transaction types. So here we have legacy transaction, access list transaction, dynamic fee transaction, and block TX, block transaction type. So transaction has this TX data, which is an interface. So any type of TX data you implement, you have to satisfy this interface. So this interface has to have certain functionalities like TX type, chain ID, access list, gas price, gas tip cap. So and to, so where exactly you're sending the transaction. And here there are like 4 implementations of this transaction, as I talked about before. So for now, let's focus on this legacy transaction, which is the default one in the sense. So any transaction has this nonce, gas price, gas to address, and value. Okay, so legacy TX is the transaction data of the original Ethereum transactions. So any normal transaction you send, so let's say A sends 5 Ether or 5 BNB to B, so this will be most likely a legacy TX struct. Okay, so we have this env here. We are back to where? We are back to this prepare work function. And we have this env, which is returned. And this generate work gives back this new payload result. So now we have this result, which ends up here. And yeah, this is the main loop of this worker. So this is an infinite for loop of the worker. So main loop is responsible for generating and submitting sealing work based on the received event. Okay, so the main loop is called from here inside this new worker function. So when the new worker is created, we have this main loop called from a concurrent function. And we also have result loop and task loop. Okay, so once we are submitting it to the result, then let's see where it is actually getting taken. So it's taken here. And inside this result loop, we have an infinite for loop again. So result loop is a standalone Go routine to handle sealing result. So once we have this result channel populated and it gives back as a block, then we are receiving a block here, and then this block is essentially mined afterwards. Let's step back a little bit and see what are the other components. So you remember this start node function, which has this backend, and eventually that backend gets converted to ETH backend, and it actually starts doing stuff. So let's have a look at this ETH backend. So what is it? It has mainly this Ethereum object, right? So this Ethereum object, so this implements the Ethereum full node service. So when you hear the word Ethereum blockchain, so this is the key Ethereum struct here. And what all things it has a lot of things. So it has this handlers, so which has this txpool.txpool. So this is the transaction pool, which is responsible for receiving the transactions, checking the authenticity of the transaction, and actually submitting the transaction throughout the network. There's this blockchain, which is the actual blockchain. There are handlers. So what is a handler? Handler is this struct which is responsible for things like fetching a transaction, fetching a block, downloading the entire blockchain history, and subscribing to the transaction so that it listens to the new transaction, and also it broadcasts the transaction to the whole network. So this is like handling all the stuff here, which is why it's called handler. And it also has the database. Okay, so back to Ethereum struct. So Ethereum struct has, as I said, txpool, blockchain, handler, and few other iterators. And it also has the database. And it also has the miner, which actually starts the mining. And it has this P2P server. So what is the P2P server? So server manages all the peer connections. So in a blockchain network, it is very important for a node to have a set of peers so that it can listen to the transactions or blocks from it. And also it can send its own transaction and blocks to those peers. So to to hold the entire blockchain network together, you need to have connection to the peer. So this is what this server struct does. Okay, so now we have seen the CMD folder, little bit of P2P, little bit of blockchain miner. I'll show where the consensus is. So if you go to, where is it? Yeah, here. If you go to the consensus folder, we have this Parlia folder and we have parlia.go. So in this file, all the consensus stuff works. So here there are some functions which might be more interesting than others. So you can see this finalize function. Let's open that. So what is finalize function? Finalize implements consensus.engine, ensuring, yeah, it implements consensus.engine. So it does things like verify the validators, check the hard forks, and it essentially does all the checks to finalize a block. Then there is this finalize and assemble. And one important function is this seal. So this seal function, it creates a sealed block using the local signing credentials. So essentially you are doing a seal of authority that, okay, this block is acceptable. So you can dig deeper into what exactly it does. It does things like it collects the voting attestations as well. Okay, so this is the consensus execution side of things, and I have also shown you the handler side of things. Okay, now let's quickly go to the user point of view, so which is essentially the things related to transaction, sending of transaction. So when you send a transaction, you use an API to send that transaction, and that API ensures the transaction ends up in the TX pool. So if I search send transaction, send raw transaction, yeah, something like this. So if you are submitting a transaction using a wallet like MetaMask, so there is a whole likelihood that it, in the end, it uses this send raw transaction to actually send it. So send raw transaction will add the signed transaction to the transaction pool. The sender is responsible for signing the transaction and using the correct nonce. So this MetaMask does that for you. So once you use it, then this TX pool, which I had shown you before, that is responsible for receiving and ensuring it passes the certain validation checks. So this TX pool has sub pools now. Before it used to be just one TX pool, which is now called, I think, legacy TX pool. But after the introduction of the blob transactions, so now we have like different types of pools. So one is for the normal transactions and the other is for the blob transaction. So that's why we have this creation called sub pool. So let's see what the sub pool are. Sub pool represents a special transaction pool that lives on its own. So essentially creating a separation between the blobs and legacy transactions. So it has two implementations, as I showed you, blob pool and legacy pool. So for now, let's check legacy pool. So legacy pool is the struct which contains all currently known transactions. Transactions enter the pool when they are received from the network, and they exit the pool when they are included in the blockchain, or if they fail certain checks, certain validation checks. If you submit a fraud transaction, that transaction will get discarded. So this is quite a long file. I'll show you one interesting function. Okay, legacy pool.add. So this is the function where most of the key checks happen before a transaction actually is included in the transaction pool. So add validates a transaction, inserts it into a non-executable queue for later pending promotion and execution. So let me show you what is a queue and what is a pending pool. So inside this legacy pool, we have two key things. So one is called queue, another is called pending. So queue is just a queue of transactions, but they may not be executed immediately. But this pending is a map which are currently processable transactions. So once a transaction enters this pending map, then it is quite likely that it will actually be executed and become part of a block. Okay, so this is the add function which I was going to talk about. So it does the essentially initial checks. So initially it checks if the transaction is already known, then discard it, then check if it is local or not. So what is local? So local transaction for a node is that if a transaction is received by a node directly from the user, then it's a local transaction. But if it is received from one of its peers, then it is not local, it is remote. So any node should not discard the local transaction ever. It might discard a remote transaction for various reasons, but it should not discard a valid local transaction. Otherwise, the user who sent the transaction just to this node, it's not fair for that user. So initially it calls this validate transaction. So it does the obvious validation checks. Once it passes the validation, then there is this check whether the transaction pool is full or not. If it is full, then we have to discard somebody because we have a limit of how many transactions we can hold as a node. So in the end, we generally discard the underpriced transaction. So if the new transaction which is received, if that is underpriced, then that gets discarded. If it is not underpriced, then we have to figure out another currently existing transaction that we have to discard. And eventually we may replace one of the currently existing transaction from the pending pool. And if this is not replacing anyone, then we push it to queue. So pool.enqueueTX. So as I said before, there is this pending variable and the queue variable. So we might push it to the queue directly. Okay, so now I've talked about sending it of a transaction and transaction getting into TX pool. Now let's see the propagation of transaction. So if I search broadcast transactions, yeah, so this is the function. If you just search broadcast transaction, that is part of this ETH protocols, ETH broadcast.go. So we have these peer structs, which is supposed to be the actual peer of a node. And this has all the information related to the peer. So this peer has this broadcast transactions. So broadcast transactions is a write loop that schedules transaction broadcast to the remote peer. Okay, so this is eventually called when we try to broadcast a transaction to the peer. And I think it ends up being here. So p.send transaction. So here we actually do the sending of transaction by doing p2p.send. And here we give the type. So this is of type transaction message. So p2p.send, that is an important function you should be aware of. So this writes an RLP encoded message. So this is not for just sending transactions, but it can send other types. So here we are giving a message code of type transaction so that the peer, when it receives, it knows it's of type transaction. And this is called from a lot of places, as you can see. So this is not just for transactions, it's also for block header message, block bodies message, receipts message, and all these things. So this broadcast transaction is called from here, peer.go. So go, we are starting a go routine here, and it is peer.broadcast transactions when we create a new peer. And this new peer is called from this handler, which is called from this make protocols. So when we create the new protocols, we create a new peer. Okay, so make protocols is called from this backend.go, which is called from this Ethereum struct. Okay, so this new function has its root from this flag.go, which is called from this register ETH service, and this is called from this function inside make full node, which I talked to you about at the very beginning. Okay, so this is like a very convoluted and a large code base and a lot of moving parts. So it will take a while before you are used to seeing what happens where at various places. So maybe just start from one single component and see what all things it does and where it originates, and that will solidify your understanding of that one component and then move to some other component. Okay, so there are like various components, like as I mentioned, transaction pool or P2P or handlers or writing of blockchain or creation of blocks, consensus. I haven't even touched upon where exactly the blocks are stored. That's another thing. So there are like various components, and another thing I have missed, which I can talk about in some other video, is about when you actually do a call to a contract. So what happens after that, and where exactly the transaction is actually executed in series. So these things I can cover maybe in some other video, or this is a take home task. Maybe you should figure out and comment where these things are done. Okay, so this is a very quick or rather long overview of the BSC code base. So one key difference between BSC code base and Ethereum code base is the non-separation of execution and consensus layers. So BSC code base itself has both consensus and execution layers, whereas in Ethereum now it has changed. So Go Ethereum is just the execution engine, but there are various other consensus engines like Prism, which you can run along with Go Ethereum. So if you have any questions or doubts, feel free to comment. Thank you.